The James Webb Space Telescope, JWST, has the potential to change our understanding of the cosmos through advanced technology and its unique location. With its 6-meter diameter primary mirror, more than twice as large as the Hubble Space Telescopes, the JWST can capture even the smallest light glimmers from the farthest reaches of the universe. This capability allows scientists to study distant galaxies, planets, and stars in ways that were previously impossible. The JWST's advanced technology supports these claims, as it can detect a broad spectrum of light wavelengths. The Near-Infrared Camera, NIRCam, is a potent instrument on the JWST designed to capture images in the near-infrared portion of the electromagnetic spectrum. This allows scientists to delve deeper into the cosmos by observing the birth of stars and galaxies up close. The JWST helps researchers understand the assembly and evolution of galaxies throughout time and provides insights into the intricate processes forming our cosmic neighborhood and beyond. Near-infrared spectroscopy, NIRSpec, is another method for studying stars and galaxies. By dissecting the light emitted by astronomical objects into its constituent colors or wavelengths, NIRSpec provides critical details about the temperature, velocity, and chemical makeup of these objects. By analyzing the spectral signatures, scientists can identify the components of a star or galaxy and learn more about the materials making up the universe. NIRSpec is essential for studying distant high-redshift galaxies, which emit light that has traveled over billions of years, offering insights into the early universe. Astronomers may determine a galaxy's age, chemical makeup, and other properties by analyzing the absorption and emission lines in the spectra. In conclusion, the JWST has the ultimate potential to transform our understanding of the cosmos through its advanced technology and unique location. By studying distant galaxies, planets, and stars, scientists can gain an unparalleled perspective on the universe and its complex interactions. The JWST is a powerful instrument providing insights into the galaxy's evolutionary history throughout cosmic time. Its mid-infrared instrument, MIRI, is the primary tool for studying the mid-infrared portion of the electromagnetic spectrum. This allows researchers to investigate various phenomena, such as star formation and the discovery of exoplanet atmospheres. MIRI's main objectives include exploring the dusty environments where stars are created, which are permeable to infrared radiation. By looking through the cosmic veil, MIRI can observe the formation of stars and planetary systems, offering valuable information about the physical processes taking place inside these celestial incubators. Additionally, MIRI is crucial for identifying and studying exoplanets by detecting faint thermal emissions from their atmospheres. The JWST uses spectroscopy and atmospheric analysis to look for biological indicators. Its primary methods include precise spectroscopy, which enables scientists to examine light emitted or absorbed by an object to determine its composition. When the JWST detects an exoplanet, it looks forward to a transit event, where the exoplanet passes in front of its home star. During this transit, the JWST closely monitors the starlight passing through the exoplanet's atmosphere using state-of-the-art instruments. The telescope records this light while MIRI dominates the mid-infrared spectrum. The JWST then analyzes the absorption or emission lines in the light spectrum to pinpoint specific compounds present in the exoplanet's atmosphere. Identifying molecules potentially connected to life requires a more comprehensive approach. Biomarkers may consist of gases necessary for life on Earth, such as oxygen, methane, and water vapor. More information and observations are needed to evaluate general habitability and any relevant biological activity. Comparative spectroscopy is another tool the JWST uses to enhance its search for life by drawing meaningful comparisons between exoplanets with similar properties. This research aims to identify patterns or anomalies in the observed spectra of various exoplanets, which could shed light on the existence of molecules or processes relevant to life. By searching for exoplanets similar in size, mass, distance from their host star, and other variables, researchers can isolate different atmospheric components and focus on potential habitability indicators. Comparative spectroscopy helps distinguish between characteristics likely linked to life and those potentially attributed to non-biological phenomena, such as volcanic activity or atmospheric chemistry. Exoplanets like Proxima B, located 4.24 light-years from our solar system, have gained significant attention due to their potential habitability. Proxima B orbits Proxima Centauri, a red dwarf star that is much smaller and colder than our Sun. The discovery of life on Proxima B would be revolutionary due to its proximity to Earth and its location within the habitable zone. However, determining an exoplanet's habitability is a complex puzzle with many variables. Proxima B, with a mass about 1.3 times that of Earth, is classified as an exoplanet similar to Earth. It takes approximately 11.2 Earth days to complete one orbit around Proxima Centauri. Nevertheless, it is not assumed that the planet will be an identical duplicate of Earth, and its precise atmospheric makeup remains unclear, complicating firm determinations about its habitability. Researchers are using the JWST and other tools to investigate Proxima B's atmosphere, examining spectral fingerprints to search for compounds that might indicate biomarkers and signs of life. The search for a habitable planet like Proxima B is a complex and multifaceted endeavor. Scientists are looking for evidence of liquid water on the planet's surface, which is essential for sustaining biological processes and is often seen as a major indicator of habitability. The planet's tidally locked state raises concerns about its possible habitat and environment, as extreme weather conditions, such as intense heat or freezing cold, could impact its habitability. Stability is also crucial in the hunt for livable planets, as habitability might be disrupted by regular seismic activity or volcanic eruptions. However, not all stability is advantageous. Proxima B's tidally locked nature means one side of the planet is always illuminated by the star, while the other is perpetually dark. The extreme temperature differences and atmospheric dynamics arising from this contrast could affect the planet's habitability. Chemical scientists examine the planet's chemical makeup for organic compounds, amino acids, and other chemicals that are the foundation for life. Life scientists investigate if the planet's biological processes are powered sufficiently by energy from its star or other sources. The cosmic machinery of life is driven by energy, which allows living things to proliferate, expand, and flourish. The discovery of Proxima B was a remarkable accomplishment, enabling astronomers to detect the faint gravitational tug of an exoplanet around its star. The Doppler spectroscopy technique, also known as the radial velocity method, is the foundation of this detection. It detects minute changes in the star spectrum caused by an orbiting planet's gravitational pull. HARPS, an instrument using this technique, achieves the precision necessary for exoplanet detection by stabilizing its temperature and utilizing a high-resolution spectrograph. Space-based programs like Kepler and TESS have contributed to our understanding of Proxima B by using the transit method to determine the exoplanet's size, orbital period, and other properties. This data provides insights into its composition and potential habitability. When assessing Proxima B's host star, Proxima Centauri, its stellar activity is crucial. Proxima Centauri is more active than the more massive and stable stars like our Sun. Frequent flares are a notable characteristic of stellar activity in red dwarfs. These flares cause powerful bursts of radiation, including ultraviolet and X-ray radiation, which can surpass the greatest solar flares by thousands of times. Such strong radiation may affect Proxima B in several ways. It could erode the planet's atmosphere, impacting surface conditions by allowing higher radiation to reach it, and long-term exposure could be harmful to life. The energy from frequent flares can change temperature distributions, disrupt weather patterns, and impact the planet's overall climate stability, potentially threatening Proxima B's environment and climate. The James Webb Space Telescope, JWST, is an unprecedented tool in the field of space exploration, designed to push the boundaries of our knowledge about the universe. Beyond its impressive hardware, the JWST represents a collaborative effort among scientists, engineers, and astronomers worldwide. Its mission encompasses a broad array of scientific goals, from probing the formation of the earliest galaxies to studying the atmospheres of exoplanets in detail that was previously unattainable. One of the JWST's primary scientific objectives is to observe the formation and evolution of the first galaxies. After the Big Bang, the universe went through a period known as the Cosmic Dawn, when the first stars and galaxies began to form. The JWST's ability to capture faint infrared light enables it to peer further back in time than ever before. This capability is crucial for understanding the processes that led to the formation of the first galaxies and their subsequent evolution. By examining these early structures, scientists hope to gain insights into how galaxies like our own Milky Way came into being. The study of exoplanets is another major focus for the JWST. Exoplanets, or planets outside our solar system, are of great interest because they may host conditions conducive to life. The JWST's instruments, particularly MIRI and NIRSpec, allow for detailed observations of exoplanet atmospheres. By analyzing the light that passes through these atmospheres during transits, scientists can detect the presence of various gases. This analysis can reveal crucial information about a planet's climate, potential habitability, and even the presence of organic molecules that could indicate biological processes. One key aspect of the JWST's exoplanet research is its ability to detect the presence of biosignatures. These are specific molecules or chemical patterns that suggest the presence of life. For instance, the detection of oxygen or methane in an exoplanet's atmosphere could point to biological activity. However, interpreting these signals requires careful analysis and the exclusion of non-biological sources of these compounds. The JWST's sensitivity and precision are vital in distinguishing between genuine biosignatures and other potential sources of these molecules. The telescope's capabilities also extend to studying the formation and evolution of planetary systems. Observations of protoplanetary disks of gas and dust surrounding young stars, can provide valuable insights into the processes that lead to the formation of planets. By studying these disks, scientists can learn about the conditions necessary for planet formation, the distribution of materials in the disk, and the early stages of planetary growth. This research is crucial for understanding the formation of planetary systems, including our own solar system. The JWST's contributions to stellar astronomy are equally significant. Observations of different types of stars, ranging from massive, short-lived stars to small, long-lived stars, provide a comprehensive view of stellar life cycles. The telescope's infrared capabilities allow it to study stars hidden behind dust clouds, offering a clearer view of their formation processes. Additionally, by observing different stages of stellar evolution, from the birth of stars to their death and subsequent transformation into white dwarfs, neutron stars, or black holes, scientists can gain a deeper understanding of the life cycle of stars. Another innovative aspect of the JWST is its ability to perform detailed spectroscopy of distant celestial objects. This technique involves dispersing light into its component colors, or spectra, to study the physical and chemical properties of astronomical objects. The information obtained from spectroscopy can reveal the composition, temperature, density, mass, distance, luminosity, and relative motion of these objects. The JWST's advanced spectroscopic instruments enable scientists to conduct highly detailed analyses, uncovering new details about the universe's structure and its contents. The JWST is also set to revolutionize our understanding of dark matter and dark energy. Dark matter, an invisible substance that does not emit light, is thought to make up a significant portion of the universe's mass. Dark energy, on the other hand, is a mysterious force causing the accelerated expansion of the universe. While the JWST is not specifically designed to detect dark matter directly, its observations of galaxy formation and distribution can provide indirect evidence of its presence. Similarly, studying the expansion rate of the universe can offer clues about dark energy and its effects on cosmic expansion. One of the most exciting aspects of the JWST is its potential to detect and study the most distant galaxies ever observed. These ancient galaxies provide a glimpse into the early universe and offer valuable information about its evolution. By observing these galaxies, scientists can investigate how the first stars and galaxies formed and how they evolved over time. This research not only helps to refine our understanding of galaxy formation, but also sheds light on the conditions that prevailed in the early universe. The JWST's observations are expected to complement and expand upon the discoveries made by previous telescopes, such as the Hubble Space Telescope. While Hubble has provided extraordinary images and data over the past decades, its capabilities are limited to visible and ultraviolet light. In contrast, The JWST's infrared observations can penetrate dust clouds and observe objects that are too faint or distant for Hubble to detect. The combination of data from both telescopes will provide a more comprehensive view of the universe and its many phenomena. The JWST's mission is also closely tied to the study of cosmic reionization, a period when the universe transitioned from being opaque to transparent. This transition occurred when the first stars and galaxies formed and emitted light that ionized the surrounding hydrogen gas. Understanding cosmic reionization is crucial for comprehending the evolution of the early universe and the formation of large-scale structures. The JWST's observations will help to fill in gaps in our knowledge of this important epoch. The telescope's advanced technology also includes innovative cooling systems that maintain its instruments at extremely low temperatures. The JWST is equipped with a large sun shield that protects its delicate instruments from the heat of the sun and helps to keep them at the necessary temperatures. This cooling is essential for detecting faint infrared signals from distant objects and ensures that the telescope can operate effectively in the harsh conditions of space. Moreover, the JWST's data collection and analysis involves sophisticated algorithms and computational techniques. The vast amount of data generated by the telescope requires advanced processing and interpretation to extract meaningful scientific information. The development of these algorithms is a critical aspect of the JWST's mission, as they enable scientists to analyze complex datasets and derive valuable insights about the universe. In addition to its scientific goals, the JWST has significant educational and outreach components. By sharing its discoveries with the public and engaging in educational initiatives, the telescope aims to inspire the next generation of scientists and foster a greater appreciation for space exploration. The data and images produced by the JWST are expected to capture the imagination of people around the world and contribute to a broader understanding of our place in the universe. In summary, the James Webb Space Telescope stands as a groundbreaking achievement in space exploration, offering unparalleled capabilities for studying the universe. Its advanced technology, wide range of scientific objectives, and collaborative efforts position it as a transformative tool in our quest to understand the cosmos. As the JWST begins its mission, it holds the promise of answering some of the most profound questions in astrophysics and expanding our knowledge of the universe in ways that were once considered beyond reach.